Okay, so on this lesson, we're going to be looking at exponential applications, which just means applications applied in the real world. So we're going to talk about growth and decay models on the front. So the general form of an exponential function, we've been talking about it, is y equals b to the x power. Base, b is your base, x is your exponent. So if b is greater than 1, which is your base, then it's called an exponential growth. We talked about that at the beginning of the unit. Okay, if your base is between 0 and 1, then it's an exponential decay. Okay, so this relationship can be extended to model situations in which the quantities repeatedly increase or decrease by a certain percentage over a specified time. So here's a formula that we're going to be using. Y is going to be the amount after t time period. A is going to be your initial amount, so starting amount. This piece is going to be your growth or decay factor, so you're going to be either adding or subtracting based on if it's a growth or a decay. And then t is going to represent the number of time, or the time. Okay, so if you have 1 plus r, that's going to be a growth factor. Because whenever you add 1 to anything, it's making it greater. So if it's 1 minus, that's going to be a decay factor, because it's getting smaller. Okay, so first example, the annual number of Lyme disease diagnoses in California has been increasing, keyword, by 40% each year since 2015, when 250 cases of Lyme disease were diagnosed. Okay, so we're going to write a function representing the number of Lyme disease diagnoses in California t years after 2015. So I'm going to start with y equals, because we have an equation or a function. My starting amount is 250 cases, my initial amount, so 250. I'm plugging into this formula up here. And since it's increasing, I'm going to, in parentheses, need 1 plus r represents your rate on the formula, and it needs to be in decimal form. So notice that our rate was 40%. So 40%, you either need to divide it by 100 or move your decimal 2 places to the left. So 0.4 would be your rate. And then we're raising it to the t power, which in this case we don't know what that is. So I'm going to go ahead and write this. I can go ahead and add my growth factor here. So I'm going to go ahead and write this as y equals 250 times 1.4 raised to the t power. So there's my function, and then we're going to use that in order to answer some questions. So we're using the function on part B to estimate the number of cases of Lyme disease diagnosed in 2025. So we're going to be able to plug into that t for the time. Now we're starting at 2015. We want to go to 2025. So that would be 10 years. So we would have y equals 250 times 1.4 raised to the 10th power, because we're talking about from 2015 to 2025. So when you subtract, you get 10 years. Okay, so we can just plug that into the calculator. So just plugging that into home screen. So we're typing in 250 times 1.4, and then we're raising that to the 10th power. So it would be around 7,231.37 cases. So we're talking about cases here, so we're not going to have a percentage or a decimal. So we will estimate, and so 7,231 cases. Okay, so then the next question, how long will it take for the number of cases diagnosed each year to reach 5,000. That's the final amount at the end, which is your y. So this one we're going to be plugging in for y. And so notice we're solving for t, which is an exponent. This is an exponential equation because we're missing the exponent. So first step is to isolate your base, an exponent. So I'm going to divide by 250. In this case, I'm just going to leave my fractions because we're not going to need to round anything until the very end. Of course, you could mark out you could reduce it or just leave it as 5,000 over 250, your choice. Okay, so that equals 1.4t. So remember we've talked about several ways of solving an exponential. I think the easiest way here would be to take the log of my base of my exponential, so we can use inverse properties to cancel it out. So what I'm going to do is take the log base 1.4 of 1.4 to the t on the right side, and then I have to do the same thing on the other side. So I'm going to do the log of 1.4, 5,000 over 250. The reason I'm doing this is because remember, inverse properties tells me since this base equals this base on the exponential, I get rid of those and I just get t on the right side. So now I'm using the calculator to plug this in order to evaluate it. So we go to just our home screen. We're going to be typing in log. We're having to change the base, so go to math, go up, log base 1.4, and then we're taking the log base 1.4 of 5,000 divided by 250. I guess, again, you could, let's see, delete that. I don't need this parentheses. Why is it doing that? Okay. Okay, so we notice we get 8.9, and that's talking about years. So my t would be 8.9 years. And you could also, if you wanted, you could also put, it would reach the 5,000 in the year 2024 if you wanted to do it that way, just adding 9 to 2015. So either way. But it said how long, so I would just put 8.9 years. Okay, let's take a look at number 2. So example 2, the value of a mechanic's car lift depreciates. Depreciate means going down in value. Appreciate means going up in value. So you have to know these key words. Depreciate means go down. So it's going to be a decay factor. So it's depreciating by 15% each year. And a mechanic shop purchased the lift new at $2,800. So writing your function, I don't know the final amount after so many years, we're starting with $2,800 for the value of the lift at the beginning. It's depreciating, so I need a 1 minus 15%. You need to change that to a decimal, so move it your decimal 2 places to the left, which would be 0.15, or divide 15 by 100 to get your answer, which is still 0.15. And we're raising it to the t power. Again, if you want to go ahead and subtract inside the parentheses there, you would get 0.85. So there's my function. Part B says you're going to use the function to determine how much the shop could expect to sell the lift for after 3 years. So we're going to plug 3 in for t for the time. So plugging in. So I would have 2,800 and then 0.85. Raise it to the 3rd power. And here we're talking about the price. So we're dealing with money. So we may want to round to the nearest cent. So $1,719.55 would be our answer. Okay, last part on this one. If the shop wants to sell the lift to replace it with a new model, when the value reaches 1,000, when should they sell? Okay, so this time we are given the Y, which is the amount after so many years. And we're looking for the time. How long? How long would it take to reach $1,000? Okay, so first step is to isolate my base and exponent. Again, you're welcome to reduce that fraction or just leave it as is. It doesn't really matter because you're going to be plugging in the calculator. So again, to solve this exponential equation, I would suggest taking the log and using the base of that exponential so it cancels out. So I would need to take the log of base 0.85 of both sides. Whatever I do to one side, I must do to the other. So the whole reason I'm doing that is because this log base 0.85 cancels with this base of 0.85, so I'm left with t. So I'm using the calculator. So I have math up log base. My base is 0.85, and then I need 1,000 divided by 2,800. And we'll just round to 2 decimal places. So that's 6.34. And we're talking about the time. So you can just write it as 6.34 years, because we can have a partial amount of a year. Okay, so you're having to read the problem, figure out which type of formula you're going to use, plug in, find the equation, and then answer a few questions. So you have to know, is it telling me the time? Is it wanting to know how long would it take to reach that final amount? Things like that. So you're looking for keywords in your problem. Okay, the back, we're going to be looking at compound interest. So compound interest, if you don't remember from going over this before, interest is earned on many savings-oriented products, and interest is owed on most loan products. So compound interest is the interest earned or owed on an initial balance and on any interest that has occurred in previous periods. Interest is paid on interest at specified intervals, not solely the principal balance. So for example, if you invest $1,000 in a savings account paying 5% annual interest, you will have $105 after 1 year. Okay, so here's our compound interest formula. If you don't know what each variable represents, make sure you know. So A is always your final amount at the end. P is always your starting amount or principal amount. R is your interest rate. Make sure it's a decimal. So change it to a decimal. N is the number of times it's compounded per year based on annually, monthly, weekly, daily. So the number of times per year, you're having to figure that out. And then T is your time. Okay, so sometimes there are a few things that compound continuously. So as the number of times the interest rate is compounded per year increases, here's the formula that you will use. So if it's continuously, if it says that word, you're going to use this formula where P is still the starting amount. E is a number. Remember, we've been using it. R is the interest rate, and then T is your time. So you're going to need to know which formula to use. Okay. So example 3, your grandparent invested $200 in an account that earns 4% annual interest. Write the compound interest equation and use it to calculate the account balance after 75 years and the length of time until the balance reached $1,000. Okay, so my compound interest equation annually, so we don't know the final amount. We know we're starting with $200, so that's our initial amount, or principal. And it says earns, that's a key word, plus. So I'm going to have 1 plus. The rate is 4%. Remember, we have to change that to a decimal. Common mistake there. So either divide it by 100 or move your decimal 2 places to the left. It should be 0.04, and then we're raising that to the t power, which is the time. Okay, so what is the account balance after 75 years if the interest is compounded? In this case, we're talking about annually. So we are just plugging that in. It should have been 0.04 divided by 1. That's why I just put 0.04, because it was just compounded annually, which is once a year. And I also just put t, because t times 1 is just t. So I'm just plugging that into the calculator. And when you plug it in, you should get $3,789.05. Okay, so it says, when did the account balance reach $1,000 if the interest is compounded? Again, we're going annually. So this time I'm given A. It's still 0.04 because it's 1. And then we're looking for T. We plugged in for this piece, we plugged in 75 for our time. So we're going to divide by 200. And then this is just 1.04 to the T. So I'm going to take the log of both sides. Log base 1.04 on both sides, so that just cancels out and we're left with T there. So we're typing in log of base 1.04 of 1,000 over 200. You should get, for the answer here, 41.035 years. Okay, so now I'm just going through the same part, except I'm going to be compounding differently. So compounded monthly, so I'll just go back to annually, that's just once a year. Monthly would be 12 times a year. So I'm going to go ahead and plug in. So my equation here would be A equals 200, and then 1 plus 0.04 divided by 12, and then I would have a 12t. So plugging in 75 for t, I should get $3,997.12. And then now I'm just plugging in, I'm going to end up with gonna have, let's see, working it out, I'm gonna have 1,000 divided by 200 equals, now I'm gonna have just gonna leave this as this because it gives me a repeating decimal there to keep it the same. Okay, so we're going to plug in. We already found this number. Now we're looking at the 1,000. So I divided by 200 at the beginning. And then this decimal is 1.0033, repeating 12t. So then when I do this, I'm going to take the log of this time I'm going to end up with a 12t. So I'm going to take the log base 1.0033 and then 1,000 over 200, and then I'm dividing that by 12. So once I get that answer, make sure you divide it by 12 here. So I'm plugging this into the calculator, dividing it by 12. You should get 40.303 years here. Okay, so weekly, how many weeks are in a year? 52. So that would change on this next part. So I'll go ahead and run it in purple. Not enough space there. So plugging in place of t, you would put 75 for the years on this one. When you plug it in, you're just plugging the whole thing into the calculator. You should get $4,012.48. Okay, so this one, you would do the same thing. You should end up with 40.251 years. Okay, so if it says daily, there are, go ahead and put 365 days in a year. So you would have the equation 365t. When you replace your t with 75, you should get $4,016.45. And then you are typing in, you're having to solve it again. So if you want to pause it and solve it and then check it, you should get 40.238 years. And then continuously, that's this formula that you will use. So that one you should have A equals, the starting amount is 200, E, remember E is a number, so just write E and you'll use the E button on the calculator. The rate is 0.04 and then T. We're replacing the T with 75. You should get $4,017.11. And then we'll try this one. So this one, when we have 1,000 equals 200, e to the 0.04t. So we're going to need to isolate the base, divide by 200. And then since my base is e, that means I'm going to take the natural log of both sides. So those would cancel. That's the whole reason I did it. So you would end up with 0.04t. And then the natural log of 1,000 divided by 200 should give you, I'll round it on my paper, but I don't need to round it on the calculator. So whenever you do it, you'll have to then divide it by the 0.04. And so your answer should be 40.236. So 40.236 years. Okay, so you can compare the different ones with your compound and frequency. So you can look at each one. So anytime you're given the y and you're having to find the t, you're having to use logarithms in order to solve that. So if you have any questions, please let me know.